We continue with the next example, corrupt.asm, which shows the dark side of memory access, or maybe some example of something which goes wrong during a memory access. Let's take a look at the source code. Basically, this source code relies on the same template that we have seen previously for the reverse program and also for the get address program. We still deal with the same array called keepNums. This time we have exactly 6 dwords which we declare inside the data section. 6 dwords which are initialized to the value 0. The code that follows inside the text section is pretty short. It begins here. Let's take a look. We first move keepNums into ESI, then we add a large number which is 10,000 in base 16. Finally, we write into the location ESI in memory the value 3. Just a technical note, in this instruction, the hint dword is necessary. The assembler will not be able to know the size of the write if we didn't provide this hint. If, for example, we don't have this hint, the assembler will complain, will not assemble this file, because it doesn't know which size to write. It doesn't know what is the size of the data transfer. This is why we have to add this hint here. So what is the problem with this program? Basically, we write to a location in memory which we haven't declared. We take keepNums and then we add a really large number, and finally we try to write to this location, keepNums plus 10,000, which is not a location that we have declared before. Maybe in some other words, it is not our memory. The memory that we really own is the memory that we have declared. For example, the things that we have inside the data section, the text section, the iData section, and so on. You might be wondering what is going to happen in this case. Let me try to explain. As an assembly programmer, at least on the Windows operation system, we have some kind of agreement with the operation system. And the agreement is as follows. We have to declare the amount of memory that we are going to use during the program, and the operation system will take care of it. In fact, the operation system has the job of giving us the feeling that we own all the memory in the computer. In fact, the operation system has the responsibility of emulating access to all the memory in the system. It gives us the feeling that we can access any memory that we want, any address that we want. In reality, this is not the case. The operation system has to do lots of strange maintenance just to make sure that we can access all of our data. To help the operation system, we have to declare the data that we are going to use ahead of time. Here, for example, we declare that we want access to 6 dwords inside the data section. However, we try to access a location which we haven't declared before, and the operation system will not be ready for this. You can think about it just like dealing with the bank. The bank always shows you the amount of money that you have. However, most of the time you cannot really access all the amount immediately. You have to wait a little bit, or maybe you have to inform the bank of the things that you want to do ahead of time, so the bank will be prepared. The same goes with the operation system. You have to inform the operation system ahead of time of the memory that you want to access. After all those talkings about what is going to go wrong, let's try to actually assemble and run this program to see what really happens. I first save the file, and next I'm going to open a console and assemble and run the program. As we can see, we get some error message which says corrupt.exe has stopped working. A problem caused the program to stop working correctly. Windows will close the program and notify you if a solution is available. Basically, the operation system tells us at this point that something bad has happened. It doesn't say specifically what happened because the usual user will not be able to understand, but we know what went wrong. We try to access a location in memory that we do not own. Let's try to fix this problem. We are going to look now at fix corrupt.asm, which is some kind of fix to the problem that we have. It is really the same as corrupt.asm. The only difference is this line. We changed the value of amount nums. Originally it was 6, and now it is a pretty large number. This time we really try to declare ahead of time the memory that we want, so that whenever we run this code, we will have no problem because the operation system already knows that we wanted this location in memory. Let's explain for a moment what we wrote in this line. The value of amount nums is a bit interesting, mostly if you have seen this kind of expression for the first time. Let's begin with the 4. Why do we have this 4? And why do we divide it by 4? The reason is simple. Every dword is of size exactly 4 bytes. As this declaration of data is about declaring dwords, if we want to declare 10,000 bytes, we have to declare 10,000 divided by 4 dwords. Next, we have to explain this plus 1. Why do we need this plus 1? That is because we begin the counting of dwords and also of bytes from the number 0. Therefore, if we want to access byte number 10,000, we have to add another dword. Think about it for a moment. The first byte is at location 0. The second byte is at location 1, and so on. This is why we add this 1. And at this point, we have exactly the amount of dwords that we need to make sure that the program will not crash, just like it crashed in corrupt.asm. Let's assemble and run this program just to make sure that it works right. Now we are going to run it. And as expected, we have no problem at this point. Just to show you that the plus 1 is important, let's omit the plus 1 for a moment and try to assemble and run the program again. As you can see, this time the program crashed. However, if we add the 1, the program does not crash. Another important thing to note in this example is the size of the output. Maybe you haven't noticed the size of the output, but this is a pretty important thing to notice, at least in this example. The output has a really large size, 67,000 bytes. it's a lot. We can see here the result, which has a really large size. Compare, for example, with corrupt.exe, which is only of size 2000 bytes. Fix corrupt.exe is of size 67,000 bytes. This is pretty reasonable because we declared lots of dwords and initialized all those dwords to be of value 0. Let's open the file with Hex Workshop. I just want to show you for a moment the amount of zeros that we have inside this file. Lots of zeros. This is why the file is so large. It contains all those zeros that we declare here with keep nums, dd, amount nums, duplicate 0. Amount nums is really large, therefore we have lots of dwords inside the executable file. This is really a waste of space. Maybe we could somehow make the resulting executable file smaller. Maybe there is a way to do it. We don't really want to keep all those zeros inside our executable file. And if we think about it, there is no reason to keep all those zeros. Maybe we could just instruct the loader of the program to put all those zeros at runtime instead of having all those zeros on the disk. As you probably guessed, there is a way to do it, which is called the BSS section. Let's take a look at fix corrupt small.asm, which presents the solution. As you can see, it is pretty much the same as fix corrupt, with one major difference. Instead of using the data section like we had before, this time it is commented out, just so you can see it for comparison. We have the BSS section. First, let's see the flags that the BSS section has. It has the readable and the writable properties. You might be wondering, what does BSS stands for? Originally, it stands for block started by symbol. But many people prefer to remember it as better save space, which is written here. It doesn't really matter what it really stands for as long as you remember the meaning of the BSS section. Whenever you use this section, you could have uninitialized data. Note that instead of having 0 inside those brackets, we have a question mark. This question mark means that we do not want to initialize this data. We don't care about the value that it has initially. Another important thing to note about the BSS section is that it doesn't have the data property. This is a bit of a technical detail and it mostly applies to the FASM assembler. However, it is important to note that it doesn't have the data property. The data section does have the data property, but if you want to have uninitialized data, make sure to not include the data property. Only include readable and writable. Let's try to assemble this program and see the result. First, we can see that we have no problem, which means that the problem is still fixed. And now about the size of the output. We can see that it has a size of only 1536 bytes, which is a pretty small executable file. Let me summarize what we now know about the BSS section. Initially, we used the data section just like this, which took lots of space on the disk. We decided that we didn't want to have all those zeros inside the executable file because there is no real reason to do it. We don't have to keep lots of zeros. We can be smarter. Instead, we use the BSS section, which is some kind of a hint to the loader of the operation system. It tells the loader, whenever you load this program to memory, make sure to leave space for those D-words, for this really large amount of D-words. Using the BSS section, we could have a much smaller executable file. The program itself, when loaded to memory, will still be pretty large. However, the executable file saved on disk will be pretty small. That's what I wanted to show you about the BSS section and also about writing to memory that you do not own. This is the end of this lecture about memory examples. I'm going to see you in the next lesson. See you next time.